Okay, so today we are going to talk about, first let me write the date here. So today we are going to talk about one of the most famous results in general relativity, and to introduce this, let me remind you of some facts about electromagnetism which you might know but you might not have realized in the words that or in the form that I'll be discussing them. So in EM, how do we find out what electric and magnetic fields are allowed? We first decide in advance what current distribution and what charge distribution we want to place. We place it wherever we like, in whatever form we want. Now Maxwell's equations are a set of coupled partial differential equations with sources. The sources are the charge and current. And then with suitable boundary conditions and picking some region where we want the solution, we solve the partial differential equation. In general, it's not easy to solve partial differential equations because they are partial. That means there are many variables, namely x, y, z and t, and the derivatives in all of them appear in all the equations. So that's why they are hard to solve. But in the case of Maxwell's equations, they are simplified by a very important fact. Those equations are linear. So if you see, they are linear in E and B. They only involve things like curl of E, curl of B, and divergence of E, divergence of B, and maybe dE by dt and dB by dt. But those are all linear in B. There's nothing like d curl of B squared or B times curl B or anything like that. So they are linear. That helps us a lot. And in the case of gravity, there are analogous equations called Einstein equations, which we haven't discussed yet, and they are non-linear in G mu nu. G mu nu is the analog here of, not exactly of E and B. Actually, E and B, as you know, come from the vector potential and scalar potential. So G mu nu is the analog of those. But whatever it is, they are non-linear in this. And that makes it much more difficult. And the general problem, that what is the most general solution to Einstein equation, is simply not solved, simply not known. But, and also of course in this course we haven't done Einstein equations, we haven't written the equations, and let me explain briefly why. The reason is that for that we have to introduce something called curvature tensor, which is the thing which embodies tidal forces. As I told you once, you can remove the first derivatives of the metric by going to a freely falling frame, but you can't remove second derivatives of the metric. And that means that it can only be with second derivatives of the metric or higher that you can find a quantity which is not removable by any change of coordinates, and then that quantity will embody what we mean by curvature. But once we go to second derivatives of the metric, there are many possible, right? You can have metric G mu nu derivative with respect to x rho, x sigma. There are so many combinations, it becomes a very complicated business. And it will take some time because we need to build up some formalism. So I'm going to skip the step of writing Einstein equations. I'm just going to give you a solution which you can assume without proof, and we'll work from there. But in the case of Maxwell equations, we have no such excuse. We know those equations with or without sources, and we can easily write them, and you know them hopefully by heart. So now I'm going to ask a very trivial question. Is there any interesting solution, so any interesting vacuum solution of Maxwell equations? And the answer, of course, is yes, the electromagnetic wave. So even if I set all my sources to 0, I get a solution which represents crossed electric and magnetic fields oscillating as it propagates. That's the wave, and it's a vacuum solution. Okay. Now even that wave solution might have made you wonder about something. It's a vacuum solution. That means there are no sources, there are no currents, there are no charges, but there's a wave. But what made the wave? Why should the wave be there? That question is not answered when we solve this kind of equation, because all we are saying is that in some region of space there's a wave. We are not solving for what created that wave. We are saying that the wave itself can exist in vacuum. And as you know, it played an important role in history, the fact that these waves exist in vacuum, in determining the structure of both electromagnetism and special relativity, because this is what told us that the light coming to us from the sun is not going through some interstellar medium, but it can actually come through the vacuum. If a wave could not be a vacuum solution, then there has to be a medium to support the wave, and that's exactly what is not there. So vacuum solution is important. But there's another, this is one type of solution. There's another one which you probably haven't thought of. I'll give in fact there are many, and it just requires slight change of point of view. So here I am going to try and look for a solution which has again vacuum solution. So rho and J are 0. Density and current. Charge density and current are 0. So here what I am going to do is set B equals 0 and see if there is a solution just for E. If you have studied your electromagnetism properly, you should immediately tell me that there can't be anything. But nobody is telling me that, and I'm going to tell you that there can be something. So let's see who's right. Am I right? Have you ever seen a solution, vacuum solution of Maxwell equation where B is 0 and E is non-zero? What? Yes or no?
B is given by E by C. The magnitude of B is given by E by C. So
No. Magnitude of B is given by E by C when? Only in electromagnetic waves. Yeah, but this is not the wave solution. I'm talking about different solution. Why should there be only one solution? I'm saying, is there another different solution? Not a wave, not with B equals E by C, but in fact with B equals 0. Is there a vacuum solution of Maxwell's equation? So let's look at the equations and then think it over. What are the equations in that limit? Rho and J is vanishing and B is also vanishing. So the equations become curl of E is 0, divergence of E is 0, and del E by del T is 0. Okay? Yes?
Yeah, so you can transform the electromagnetic solutions through a Lorentz transformation to get a solution where B is 0, right?
No, not unless they are, because then only at a point. It's a wave, right? So you cannot make the wave have no B.
So E dot B is an invariant for the field tensor, right?
Yes.
And E dot B
Therefore,
is
B
0
can't
for
be.
the EM wave.
E-
Right, E cross. E dot B is 0 for the EM wave.
No, that's fine. So I'm not saying you can't make B 0 at one point, but you can't make B 0 in a region. Because B and E are changing constantly. So whatever Lorentz transformation you have in mind, that will take a fixed E and B and it might make B to 0. But it won't, that also I'm not completely sure, but it certainly won't make it 0 everywhere. So these are the equations we want to solve, and the most obvious solution which is staring at you is E equals 0. But let's try to be a little systematic. So the last equation gives me E is independent of time. So let's just say static. That's the first fact from the last equation. Then we go to the first equation. When curl of something is 0, that thing is just gradient of a scalar. So, and we by convention put a minus, and that's our famous electrostatic potential. And then look at the middle equation. We have del squared phi equals 0, which is Laplace equation. Yeah? Okay. So again, obviously phi equals 0 solves it, but maybe there's a situation where something else solves it, and let me make that situation for you. So first, let's forget all that we are doing today and remember something about electrostatics, which is that if there was a charge Q, then there would be a everywhere radial electric field. And the field would be given by E equals Q by 4 pi epsilon 0 R over R vector square. This formula you surely know. Yes?
So we are trying to find, so the source terms are 0 in all space.
I'm coming to that. So I'm recalling for you that this is a solution when there is a source term, when there is a charge. Now supposing I ask for a solution in a region of space which doesn't include that point, the origin.
The source including.
I
mean that does not include the source.
That doesn't include the source. So for example, I take my three-dimensional space, but I ask for a solution which is valid everywhere except in a small sphere around the origin, a small sphere that I call S, and here let me draw a large sphere that I call capital S, that represents the infinity of the space. So in this region, this is actually a very good solution of this equation, source-free equation, because the source isn't in the region. Okay, so there can be vacuum solutions as long as we restrict ourselves to a region. Now, you might think I'm making some analogy with gravity. That's not my main purpose. My main purpose is to show you that what we mean by vacuum solution depends a lot on your choice of region. So actually now from this example, you can see that I can take a lab and put any currents and any charges anywhere, and then I can take a little ball in between all of those, which is not intersecting with any of the charges or currents. In that ball, I have a vacuum solution of Maxwell equations. So it's just good to keep in mind that as long as we stay away from sources, we can have vacuum solutions. Actually, of course, if you see this solution being actually this sort of field, there is no doubt that you will conclude there was a charge hiding in the center. But if for some reason this is missing from your space, or this is simply not allowed to be entered, then you can just say, well, there is such a solution and Q could be anything, any number, and the solution is still there.
Is this because this is written in differential form and this is local?
Yes, it is exactly that. It's because these are differential equations which are local. So they only, if they are solved in a finite region, they don't actually know what's going on outside that region, other than through boundary conditions. Now that boundary conditions might also make you wonder, because look, the equation we are basically solving in the end is this one, divergence is 0. And you may say, well, how is this working? Because if I look at that solution, I can just do it there. There's obviously a flux of electric lines going out through this sphere at infinity. And this integral, which is also 0, we know by whatever it is, that this is integral of E dot dA, which is the flux through this sphere. So you may wonder that how come this is obviously non-zero, but I'm saying that this is 0. And the answer is, of course, that actually this theorem says that if I do this over some volume, then this integral is over the boundary of that volume. But this volume has two boundaries. One is the big sphere and one is the small sphere. Okay? And so actually this is nothing but flux out of the big sphere S minus the flux into the small sphere, S, this one. So the flux is coming in here and going out there, and it's the same. Of course, the field lines, as you know, are weakening by inverse square law, but the size of the sphere is increasing also because the sphere area goes like r square. So they compensate each other. So the flux there is the same as the flux here. That's why this integral is 0, and that's why this is consistent with del dot E being 0. So everything is clear. Okay. So this is just a way to think about differential equations, that you really can focus on regions. Everything doesn't have to be covering all of space. You can get interesting information in a region. Yes.
So the normal vectors are pointing outwards for
Yes.
both spheres.
Yes.
So then how is
Because the boundary, so the theorem, this is, I don't know whose law, Stokes' law, Gauss' law, somebody's law. Okay, whoever's law, it doesn't matter, says you should do this over the boundary of V. Boundary of a space in mathematics is the space of one lower dimension where it ends, but that boundary comes with a normal direction. And if you see this outer boundary, the normal is out. The inner boundary, the normal which points away from my volume, is in. Okay, I can choose the normal to be in or out, but my point is that the flux, when I count the flux through the whole thing, I have to treat the normal as going out of my volume. Okay, therefore I get a minus sign here. If I got a plus sign, then I would be in trouble. This is a minus sign.
I think it's a convention.
It's not just a convention. The relative sign of this and this boundary is negative. Okay, you can see that this sphere, if you say the normal of my sphere is always out of the sphere, then this normal takes me out of my volume, but this normal then takes me into my volume. It's not symmetric situation. Okay, so there's a minus sign. However you look at it, there's a minus sign. Mathematicians are fond of saying that the boundary of this space is that sphere minus this sphere. And then of course you may ask, what does it mean to be a sphere minus another sphere? Boundary is a concept which comes with some signs built into it. Yeah.
So here between the two spheres we have the field itself as diverging.
Yes.
And how do we have the divergence as 0?
Oh, because yeah, just it is. Because really the divergence is actually from there.
From the point, yeah. I get that.
Yeah. It's because it's diverging in angle, but it's also falling off in 1 by r squared. That's why del dot
If we
E,
consider the
for a
two-
point charge, del dot E is a delta function here, right? So we always knew that del dot E is 0 here.
Okay.
So it's only non-zero from where it's
So,
diverging.
but if we take the all space, we
Ah.
have through Gauss's law that
Yeah.
del dot E would be minus q by epsilon. Right?
Yeah.
Not the delta function.
It's not increasing.
No, integral would be
yeah,
q, but
okay.
del dot E itself would be q times, if it's a point charge
Yeah.
or a localized charge, it's a delta function which has no support outside that region.
Okay.
Good. So very simple things. Now we are going to change gears. Any questions though? I think it's just good to think about these kind of things. Now we are going to change gears and go to gravity. And I'm just going to announce for you a very famous metric of space-time, which is given in the coordinates t, r, theta, phi. And these names are chosen because t is supposed to remind us of time, and it has to be a time-like direction, which comes with some negative sign. And r theta phi are, of course, we know that r theta phi are normally the directions of spherical polar coordinates. But here you should just think of them as a radial and 2 angular directions. Okay, that interpretation anyway will become clear when you see the metric itself. So first it has a term 1 minus rs over r dt squared. Then it has a term 1 minus rs over r to the minus 1. Actually, let me write it this way once. Plus 1 over 1 minus rs over r dr squared. And then plus r squared d omega squared, where d omega squared is short form for d theta squared plus sine squared theta d phi squared. Okay. Now, this is not such a difficult metric if you think about it. There are many things you can already say. One of them is this d omega squared by itself is a metric of a two-dimensional space, not space-time. And what space is that? You have seen it. We have done it explicitly. It's the two-dimensional sphere in polar coordinates of the sphere, theta and phi. Phi is the azimuthal angle and theta is the whatever other angle is called. Theta goes from north pole to south pole, 0 to pi, and this one goes round the sphere from 0 to 2 pi. And because the latitude circles shrink at the top and bottom, that's why there has to be a sine squared theta. It reflects that fact. And it has to be exactly like this. If it was sine cubed or sine theta or some other thing, it would not make a sphere. It's exactly this which makes a sphere. And I think that we gave an exercise to even prove that. You simply embed, take the three-dimensional space and solve the equation x squared plus y squared plus z squared equals 1, and you get this metric. There's nothing to it. Okay. So this part of the metric is easy. These two are non-trivial because they have what you might call a modifying factor or function, and that function is also, however, easier than it could have been because the function in the metric can in principle depend on all the coordinates t, r, theta, phi, but this function only depends on r, and this also. Not only that, this function is 1 upon that function. It could have also been an independent function, but it's actually the same function just coming in the inverse. One cute thing is that when I calculate the determinant of this metric, these two will cancel out because these are going to come in diagonal entries. So that's a cute fact.
C square is also like 3.
Good. C squared. There's no C squared right now because I have not, there is no, okay, good. Maybe I should have put C. Thank you. C should be there. So CT is my coordinate always. So C squared dt squared. Yes. Now, actually, what will happen, and I'm just delaying it, is that at some point we'll start working in units where C is 1. And in all of research, we work in those units, and that's why I keep forgetting the presence of C factors. But they are very important to help us understand the physics in the beginning, and this is the first course. So we should keep them for a while. So that's the metric. Okay, so who found this metric? It was Carl von Schwarzschild, very long name. If you break it up, it has an interesting meaning in German. This word means black, and this word means shield. It's the same as the English word shield, and Schwarz is the German word for black, the color. So that was his name. He discovered this in published it in January of 2016, and in May or June of 2016 he died in a war, and that was the end of him. But not the end of his solution, which is still the most cited solution of Einstein equations. It's in a way quite amazing that Einstein himself didn't find it. I mean, he found the equations and he didn't really present any solutions, as far as I know. Later he did, but the first interesting solution, if you like, was this. Now, of course, probably what Einstein must have done is what we already did, which is to find an approximate solution, which describes the weak Newtonian potential. And what we'll see is that that solution we found is actually an approximation to this one, and it will help us to understand what is this number Rs. But before your question, let me say at this stage, Rs is a free parameter. Which means that this solves Einstein's equation for all values of Rs. Okay, this is maybe in a way slightly, don't take it too seriously, but slightly analogous to the fact that this vacuum solution was working for any value of Q because Q was not in the space, so it didn't really matter. And it has dimensions. That should be very clear to you, that if R is really a radial coordinate, then Rs has dimensions of length, so that Rs over R can be dimensionless and can be added to 1. Yes, your question.
The signature of the metric is weird because beyond Rs, that will become equal to that.
Slow down. Let me give my lecture. You're completely right. It is weird. It's just full of weirdness. but we need to do a lot of analysis before we can ask those questions. So first I want to highlight a few properties of this which are very striking. Property 1, the metric is time independent. Any metric always has the term dt squared. That doesn't make it time dependent. What we have to look for is the coefficients, whether they are time dependent, because you can write this as a matrix which has diagonal this thing and that thing, and then you can ask whether it's time dependent, and of course there is no visible dependence on time at all. Now when we write a space-time that's time independent, it's really a bit jarring to understand even what it is. It means it's a space-time which has always been there. It is not an evolving space-time. Nothing's happening in it. It is just there. Since the beginning of dawn of creation till future infinity, it's just always there. Okay. Obviously, it's some kind of idealization, but that's what it is. It's an eternal space-time. Okay. And of course, it has a name. We call such space-time static. So there's an analogy with electrostatics that it's called static for the obvious reason. Coefficients are time independent. Now you may object that I can simply, I've told you many times that we can change coordinates as we like without changing the geometry. So what if I just replace r by r times some function plus some function of t, then I'll manage to make everything time dependent and we'll be in a mess. Okay, so it turns out that so it turns out that in that case, you would be able to do some analysis to show that it can be brought into this form, which is time independent. So in a way, when we say a metric is time independent, we mean that there's some choice of coordinates in which it's time independent. That's a loose way of saying it. We'll see later in the language of killing vectors that there's a more precise statement, namely it has what is called a time-like killing vector. Okay, so we'll see that later. That will give a more coordinate independent definition of time independence. But for now, it's in this form, and in this form definitely it's time independent. Good. Okay, the second property, which is also very nice, is that its angular dependence is completely contained in this term, and this term is completely depends on only this combination of two angles, and this combination defines a two-dimensional sphere. Okay, and this is the metric of a unit radius two-dimensional sphere, but since r squared is in front of it, it makes it the metric of a sphere of radius r. But a sphere of radius r is a very symmetrical object, because you can rotate around all axes and you get the same thing. So therefore, the metric is spherically symmetric. So here we are seeing a space-time which is spherically symmetric. That's very simple. That could have been spoilt if this was, say, not the metric of a perfectly round two-sphere, but maybe the metric of a sphere which had a dent in it. Take a metallic two-sphere, hit it with a hammer, you will get some dent or some bulge. Then this won't be its metric. This is a metric of a completely smooth, uniform two-sphere, exactly the round one. If you had some deformed two-sphere, then this would not be spherically symmetric, and that would be, then it would be more complicated. Okay, so it's spherically symmetric. Third property, as r goes to infinity, the metric becomes this, because this term goes to 1, this term goes to 1. Now what is this the metric of? Flat space-time, Minkowski space-time, because this whole combination is nothing but our old friend dx squared plus by squared plus bz squared. Just written in spherical polar coordinates. But it's only in that limit that dr squared combines with r squared, because otherwise dr squared had this factor and this doesn't have any factor. So you can't combine this and this to get rid of the spherical coordinates unless you go to the limit where r is very large compared with rs. In that limit, you can actually combine those and you can just think of this as the metric of ordinary Euclidean three-dimensional space. Then you add the time and you get Minkowski spacetime. Minkowski spacetime is nothing but minus dt squared plus the metric of Euclidean space. Okay?
So this, I mean, 3-parameter array. So actually, that, I mean, we can use that to compare. I mean, what is larger? And
Exactly. It's a distance scale. So the correct statement. Thank you very much. In this one, it's a distance scale associated to the metric. We still don't know what physics it describes. This metric. It's a mathematical solution, but these are three properties. And this property also all have given a name: static, spherically symmetric, and last one, this is called asymptotically flat. Or you can say asymptotically Minkowski, but asymptotically flat is commonly used. Okay, so it means that whatever this space-time is, when you're sufficiently far away from it, you don't see anything. It's something whose gravitational field falls off, and that fall off is due to these 1/r factors here, such that for sufficiently large r, it's gone, and we are back to Minkowski space. This suggests a localized object, right? And the localization size also is suggested is Rs. So that's already interesting. Now let's do a more serious calculation. Okay, before I do any calculation, let's leave the metric here. And let me tell you a theorem which is quite difficult to prove. It's even in advanced courses, one doesn't usually spend too much time proving it. It's called the Birkhoff theorem, and it's a very important result in 3+1 dimensions, because we can also study this kind of space-time in other dimensions like 4+1 or 9+1 or anything. A metric, a vacuum solution. When we say solution, we always mean of Einstein's equations, which is 1 static, 2 spherically symmetric, and 3 asymptotically flat. Is unique. That means it is the Schwarzschild metric. The Schwarzschild metric is the only metric which is all of these things. So it's not that he just found one solution, he found the solution. This theorem was proved after his work and presumably after he died also. But the theorem says that if you want these conditions to be satisfied by a metric, and it's a vacuum solution of Einstein equation, it has to be this and nothing else. Of course, when I say nothing else, there are always possibility to change coordinates in this, but it has to be this in some coordinates. So it's very unique. It's very, very striking that way. Okay, and this is the reason why it's not just a solution of Einstein equation. In some sense, it's the kind of default that one always discusses. There are a million reasons to discuss it, and we'll cover many of them. But what is missing so far is what is the object that this describes. And that's not something you can immediately read off from the solution. You have to do some physics about gravity. This doesn't even say anything about gravity. It just says this is a space-time. Okay? But what gravitating system, what object with a mass and with some distribution, yes?
Isn't the approximate metric we used satisfies all three of them?
Very good. Nearly, and we are, it does actually. It does satisfy all three, and therefore actually, by a very good point, by Birkhoff's theorem, it should actually be the same as that metric in some way, and in fact it is, and that's my next point. So let's recall that we had an approximate metric for a weak static Newtonian field Newtonian potential. But this was an approximate metric. We never said that this solves Einstein equations, we just made it up. That one we can't tamper with other than changing coordinates. This one we can do anything we like as long as we remain linearized in the potential. We can drop, as long as we drop higher powers of the potential. So for this, the metric we found was ds squared equals minus 1 minus 2. So I'm assuming that phi g is now set equal to minus gm by r. Newtonian potential for a massive object of mass m. So that is the Newtonian potential. So then we get this. Then we had 1 plus 2gm over c squared r. And then we had here dr squared. So actually I wrote it as dx squared plus dy squared plus dz squared earlier. But as you agree, we can just write the same in spherical polar coordinates. Now these things look a little bit similar, but there are a few issues. One of the issues is that this prefactor multiplies the whole 3 metric, while in this case it multiplies only dr squared and not the rest of it. Okay. The second issue is that this factor is not the same as this factor. This is 1 upon something, this is just 1 plus something. Okay, good. Now, of course, we can solve, it turns out we can solve both issues nicely. One of them involves a change of coordinates. So I'm going to actually, in this approximate metric, I'm just going to rename my r as r prime and then define a new r such that that new r will be the one of this metric. Okay, so let's prove that now, that it actually goes to that in 2 steps. The first step is to get this term away from this bracket so that it can be all by itself. Okay, so for this we are going to define just a constant shift in r. R prime is r minus just that. Okay. Now, what is the, so everything is r prime in this metric. And remember that in this metric, we are free to drop anything which involves a power of phi g over c squared. Linearized. That's very important. So, in that, working in that approximation, I put this in. Now, I notice a bunch of things. First of all, here I should put r prime is r minus gm by c squared. Right? Now, when I take that r out, I'll get a term gm by c squared, a series in gm by c squared, which is going to multiply already a gm by c squared. So that whole series is irrelevant. So in this term, I can put r prime just equals r. This shift doesn't make any difference. Is this clear? This is the people are nodding, not everyone though, but this shift doesn't make any difference in this factor and this factor. That's good. Not only that, it doesn't make any difference in this factor because dr prime is dr because that's a constant. So we are getting better. Only problem is there's this factor. What does it do there? So let me focus on that term, this bracket and this term. So it's 1 plus 2 gm by r, and then r prime squared is r minus 2 minus gm by c whole squared, and then d omega squared. Okay. Now I want to manipulate this. The first step is c squared. First step will be to take r outside. So it's r squared. This is 1, and here there's an r. And here also. Okay. The second step is to expand this power of 2. You get 1 minus 2 gm by c squared r. And then you drop everything else by the same argument that we are working in linear approximation. So this is the same as this. Now what is the product of this and this? 1 minus this whole thing squared, but we are dropping that thing squared, so it's just 1. So this is 1. So we've got what we want, r squared d omega squared. Okay, so this metric now, with these new coordinates, I can simply close this bracket here and write this term separately with the coordinate r. And now we can continue our comparison. Was that clear? It's in the notes, you can verify it for yourself. Everything rests on the fact that this metric cannot be relied on to higher power in Newtonian potential, because we never took into account higher powers. We dropped them right early on. It's the metric for a weak potential. That is not the metric for weak anything. That's the metric which solves the Einstein equation. This is a metric for a weak potential. So by some massaging and changing a simple change of variables for r just by a shift, I've got it into this form. And now the last step, I think you can see it coming. This thing is exactly the same as 1 upon 1 minus 2gm by c squared r in the approximation. Because 1 over 1 minus x is approximately 1 plus x, plus terms of higher order in x. So I can replace this by that. And now you see I have exactly this metric. As long as I identify Rs equals 2gm by c squared. And what's happened here is that this mathematical parameter Rs, which by the way has a name, it's called Schwarzschild radius. Radius is not the radius of anything so far, but it's called a radius because it's just a parameter of the same dimension as the radius. On the other hand, here we had the Newtonian potential for a body of mass m, a physical body of mass m. And g and c are constants of nature. Okay, and so what we have said is that the Schwarzschild radius is nothing but the mass of the object scaled by some constants, which actually convert the mass into a object of dimension of length. If you see g by c squared has dimension of length, you can verify that. Sorry, g by c squared times m has dimension of length. And if once we make this identification, we can write this metric in a more standard way as 2gm by c squared r, and here 2gm by c squared r. And now we can say that this is the metric, the space-time for any static, spherically symmetric body, physical body of mass m.
So we actually exploited the uniqueness of this metric to derive this.
Where did we exploit the uniqueness? Yeah, I guess in a way we did.
You assume given this condition, under this condition, there can be only one submetric.
Yes, that.
So here using the approximation, you found one, and you said this is the only possible.
Well, actually, good. We found one, and we got it into that form.
Yeah.
Once we got it into that form, then we realized that actually in that form, it has to be exact, not approximate. So there we use the uniqueness. Exactly. Yes.
You only showed that this should be approximately equal to Rs.
Good. So yes, that's a very good point. It could be that this is equal to Rs up to some corrections of powers of Gm, because that was approximate. Now that actually cannot be proved by the calculations I'm doing, but it's true that this is exactly equal to Rs, and that is proved by a different calculation. That's proved by a calculation in general relativity which evaluates the mass of this space-time. So there's a kind of, it's very puzzling how to evaluate mass of a space-time. But the one guess you might have is that whatever it is, we should go to, first of all, it should be static, otherwise it's not even a object, it's just an evolving space-time. If it's static, it doesn't have to be spherically symmetric. I should set up a sphere at infinity and measure some energy there, and then hopefully I find the mass of the object. that calculation, which is called ADM mass, gives the same identification and it's exact.
Why does it need to be static?
Well, you could have the mass of a non-static space-time, but you can't just think of that as an, well, okay, it doesn't have to be static. It could be an object that's burning or evaporating or shrinking, you're right. It could be collapsing star. It would still have a mass, but you have to be a little careful because its mass will be varying. Let's say it's a star which is giving off a lot of gas or something. Then, I mean, its mass will, emitting stuff, then its mass will change with time.
Also,
The way to understand this mass is usually by evaluating some conserved quantity at infinity, but in time dependent situation, as you know, things are not conserved.
and also by like the mass of space-time, it is the rest masses.
Yeah, this always we should think of as the rest mass, correct. And in fact, since it's static, you see, if it was moving, this couldn't be the metric. You can actually take this metric and boost it to be a moving metric with a velocity v, and then you would have the metric of this spherically symmetric body, which is just moving at constant speed, and there's nothing interesting. It's just the same object in a different frame. So you're right, it's the object at rest. Okay, so this is something really very, very beautiful, and every time I discuss it, I find it just more beautiful. It's so simple. I mean, you can hardly say any calculation I've done in today has been a difficult calculation. And even conceptually, what did we do? We just said that this is the metric coming from some Einstein equation that you have to assume. After that, everything fell into place on its own. This metric we arrived at long ago by considerations that that general theory of relativity and its geodesics should reproduce Newtonian gravity in some leading approximation. So everything kind of fits logically. But the beautiful thing now is that with this metric, I can calculate the motion. Let's say now let's think of this as the metric of the Earth for a few minutes. All I have to do to make it the metric of the Earth is to put m to be the mass of the Earth. There's nothing else I have to fix. Once I say m is the mass of the Earth, this becomes the metric of the Earth. Okay, and now I have to only study geodesics in this metric to find out how any test particle, whether massive or massless, whether photon or electron or anything, or even a small rocket ship, will behave in the gravitational field of the Earth. So in a way, Kepler's laws are gone. This is the replacement. This metric and its associated geodesic equation should give me all possible orbits, like for example, elliptical orbits. Now they might not be exactly elliptical. We don't know what the geodesic equation will give, but we know that in leading order it should reproduce any old law like Kepler's law, which is already established. It will, but it will give corrections. Then we can also think of an object that's just infalling straight to the Earth. That geodesic, that will be called a radial geodesic. We can think of like a comet which has a hyperbolic orbit which bends around the Earth and then flies away. That's another kind of orbit. All of those must come from solving some geodesic equation with different initial conditions. That really unifies the subject in a very beautiful way. So now the last thing to say is, what is the allowed range of R? And the question, of course, is kind of shouting at you from this. What happens? So if R is very large, we are good. It's almost flat. As R comes in from infinity, this thing starts to get these factors, and these factors grow in magnitude as R becomes smaller and smaller. And they bend the space-time into this metric, and that's the gravitational field effect, and that we expect. But at some point, if we extrapolate, we'll find R to be equal to 2gm by c square. Sorry? Rs, yeah, of course. So exactly what happens at the Schwarzschild radius. Yeah. So it's weird because this goes away. That's very weird. Only yesterday we learned that this is the component which tells me the redshift. So apparently in this limit, there will be infinite redshift. Time will stop. Time just stops. What is that? But secondly, this blows up. Huh? this becomes infinite. What is that? So there are answers to these questions, and by the way, it took people many years in those days to figure out the answers. Again, Einstein, among others, was confused about what all this means. There were a lot of arguments, and in those days, these kind of arguments could range, could go on for years or decades, while also world wars were being fought in between, and Schwarzschild was going off and getting killed and all that. So it was more complicated than things are now in a way. So eventually it was settled, and I'll tell you the resolution, but not right now. You're most welcome to go and read about it on Wikipedia. But there's a simpler resolution, which is the following. What is Rs for the Earth? It's a calculable number, 2 times known constant, and mass of the Earth, whatever it is, some number in kilograms. Yes. So you do the calculation and you find, so the Earth is 6 times 10 to the 24 kilograms. And if we put that in here, it looks like a huge number, but unfortunately it gets defeated by the c squared, which is large, and the g, which is also small in MKS units. And when you do everything, you find that Rs is just 8.7 millimeters. And now you face the interesting paradox. We are saying that this space-time describing Earth starts behaving weird when we take the distance from the center of the Earth to be below 8.7 millimeters. But this is a solution of vacuum Einstein equations, and inside the Earth we are not in a vacuum. Earth is made of stuff. So it's not valid simply. So this solution is valid where? This is why I brought in the electrostatic analogy. It's strictly where R, so the solution is valid for R greater than R0, which is the physical radius of any body. The one which is few thousand kilometers for the Earth, the radius of the Earth. Okay, because this is a solution in vacuum. Of course, outside the Earth you have atmosphere, but you can say, okay, atmosphere very thin, it's not, you can say the solution is good outside the atmosphere, maybe 10-20 kilometers up. But you can't say that this solution describes the Earth or any such thing when you go inside the Earth's crust, because then the Einstein equations pick up a term which is the mass of the matter in the Earth. Just like the Maxwell equations, if you went into the origin, would have picked up the charge of that source. So the source is there inside the Earth. And so we use I use R0 for the physical radius of the object. And you can only use the solution when R is greater than R0. And so this problem that you are seeing in the solution, as far as the Earth is concerned, will not ever arise. You cannot simply take this solution below R equals R0. You cannot even think of going near RS. Just the wrong, then it's the wrong solution. There is some other solution which will be the solution of Einstein equation with matter, and it may not look like this, and it may not have this property. In fact, it doesn't look like this, and it doesn't have this property. You know also similar fact in electrostatics. If I have a charged sphere, I can solve my equations easily outside. I can't extrapolate that solution into a solid sphere, because once I come in, the field actually drops instead of growing till I reach the center, because that charge is constant density. And Earth we can approximate, it's bad approximation, but you can say also it has constant density. So let me close with a table which ChatGPT kindly generated for me, which gives you the interesting quantity that is so let's start with an object, and let's ask what is Rs upon R0. Schwarzschild radius of that object divided by the physical radius. In the case of Earth, that's 2 millimeters divided by radius of the Earth. So let me list what I found. For the moon, this ratio is 6.3 times 10 to the minus 11. It's a dimensionless number. Okay. For the Earth, it is 1.4 times 10 to the minus 9. That is this 8 millimeters divided by radius of the Earth. For Jupiter, it is 4.0 times 10 to the minus 8. For the Sun, it is 4.2 times 10 to the minus 6, getting a little bigger. And there are two more entries, Sirius B, which is a white dwarf. You know, these are very dense objects formed when stars collapse. Now it's 5.1 times 10 to the minus 4. And for a neutron star, which has twice the mass of the Sun, I suppose you know this symbol, M of circle with a dot in it means mass of the Sun, used in astronomy. So it's just twice as dense as as heavy as the Sun, but you know what its size is? It's just 11 kilometers. This gives you an idea how dense it is. It's two suns compressed into 11 kilometers. Okay? And with such a phenomenally dense object, this is just 1/2. The Schwarzschild radius is half the size of the object. Okay. Now let's tell you that for a black hole, the Schwarzschild radius is greater than, this ratio is greater than 1. And so the only, and in fact that's what makes it a black hole. And this is a list of all objects that are known to exist in the universe. So let's draw a picture. If this is the Earth, then this is R0 and here is Rs. So Rs isn't a real thing, it's just a mathematical thing. There's no property, it's not a property of the Earth at all. Right? I told you the solution is not valid there. You can just draw a dotted line of this size and say that's where it would be if the solution was valid there. Okay. So this is Earth. But if we now go to neutron star, then we have this is R0 and then here we have this is Rs. It's still a fake sphere. It's still not valid. It's because it's still inside the matter distribution, but at least it's pretty close. And for a black hole, it's the other way around. Whatever the matter distribution R0 is less than Rs. And then you have to face the fact that as you approach this object, you hit the Schwarzschild radius and you're still in the vacuum solution. So the solution is still valid. Okay, because the matter of this object supposedly is compressed much tighter. So you need something very, very dense, incredibly dense. Okay, and then only for this you have to deal with that question. Or another way of saying it is, when we want to deal with that question which he raised, that what happens, all of you raised, when R goes to Rs, what happens when this goes to 0 and that goes to infinity? The question is only relevant to one kind of physical object, which is a black hole, and it will turn out that exactly this question points to the existence of black hole, but not in an obvious way. Actually, it turns out that nothing goes wrong at R equals Rs. All that's happening is that our coordinate system goes bad and we have to change to other coordinates, then we can go very nicely through this place. And yet, this place, this sphere, has a meaning. It's the sphere called the horizon of the black hole. I'm just telling you some pop-sci words, not teaching it yet, such that signals cannot come out from once you're inside that. But that stuff we'll leave for later, much later. Yes. Question? Yes.
So this, when I wrote the metrics of the Earth,
Hmm.
we started off by saying that it will be only gravitational
No, we started there with a weak potential, yes, but we also started here by saying this is an exact solution, except we don't know what is RS. Then by comparing them, by getting that into this form, we realized that we have a spherically symmetric solution, approximate solution, but actually there is a spherically symmetric exact solution. So it should match that solution. The matching of parameters is suggested that RS is 2gm by c squared, but not guaranteed because there could have been higher order corrections. But again, you can assume without proof that that is the matching. Yes.
The RS by R ratio for non-rotating black holes or like Schwarzschild black holes will be equal to 1 or will it still be equal to 1?
It's greater than 1 for all black holes. Rotating, speaking of rotating, this is not a rotating solution. A rotating solution is different. It's not spherically symmetric anymore. When something is rotating, it's only axisymmetric because there's a preferred axis of rotation. And as you know, the Earth bulges near the equator and squashed like that. It's not so important whether it bulges or not. What's important is it has a unique axis of rotation. So the space-time metric of such a rotating object is not the Schwarzschild metric, it's something else. It's called the Kerr metric actually, Kerr. It's much more difficult to write. So right now all the objects we are discussing are just non-rotating because it's much easier.